Hello, we're back talking forces tonight. And when we start talking about forces, we have to look at a couple of things. And of course, you can't talk about force without talking about my favorite movie of all time, Star Wars. And if you follow, you know that Star Wars is like a 6-movie set. And I, of course, have my favorite. My favorite is The Empire Strikes Back. And of course, this quote that we have tonight is actually from The Empire Strikes Back, where Yoda is actually talking to Luke, and we're trying to lift the X-Wing fighter out of the swamp. And Yoda says, "No, try not. Do or do not. There is no try." And so he says this because that's the epitome of what comes down to physics. You really do have to try. And so this gets kind of confusing. But bear with me and make sure that you kind of follow along and be very careful on how you do things. It is about trying, and it's about making sure that you understand all of the different forces that are going to impact an object. So tonight we're going to talk forces, and we're going to work specifically with those contact forces that we talked about in the last video. So now we're going to talk about these contact forces. First one I want to talk about is gravitational force. Okay, gravitational force, and by the way, we're looking at things now from a standpoint of a free body diagram. Okay, so this is my free body diagram. Typically I have a block or some object, and I want to examine the various forces that are acting on that object. Okay, and so I usually put a dot, and the dot represents the center of my mass, and then I draw an arrow. Okay, and so this arrow that goes straight down, this arrow right here, this green one, is going to be my gravitational force. It's the force due to gravity, and I usually label it in class whenever I do problems as F of G. Okay, it's the force due to gravity. Now it has magnitude. Okay, this is one of those arrows that its magnitude is its magnitude. Okay, it's found by taking the mass of the object times 9.8. Okay, so we're essentially finding the weight. Okay, this arrow represents the weight of the object. And it always acts downward, okay? It will always act downward. So that's the first force that we always like to draw anytime we draw a free body diagram. So even if we have a block, here, hold on, let's get this better. If we have a block sitting on on a plane, okay? This block has mass, it has mass, which means it has weight, and so there's an F of G acting that direction. Another situation might be something like maybe we have a rope connecting to 2 blocks, okay? And this block being a lesser mass than this one, meaning that the block here is going to be going up as this block is going down. And so we start to look at this and we say, well, this block here has a mass, and this block here has a mass. And notice that I wrote my arrows different because, again, the arrows represent the size of the object, the weight of the object, the magnitude of the object. And so that's how we kind of look at gravitational forces. Always acting down, always arrows representing the size, okay? Actually, that's my force at a distance. That's my added distance force. Okay, let's talk next one. Next one is the normal force, okay? The normal force is this one right here. And when I look at a normal force, it goes back to Newton's third law of motion. So in other words, I have to have 2 objects interacting with each other. So I have a block that is acting on the incline, but the incline is acting on the block. And so there's a force that the incline acts on the block. Now, essentially, we have to have some balance here. And so we talk about it in terms of a normal force. And this normal force is kind of my arrow that represents how much force was the incline acting on the block, okay? So you'll always see that it's perpendicular. That's a key thing. It's always going to be perpendicular to my surface. When I'm on an incline like I am here in this picture, my surface is at a slant, so my normal force acts perpendicular again to my surface. If my surface was a flat surface and I had a block sitting on my flat surface, my normal force would act opposite my, or perpendicular to my surface, but it acts directly opposite my weight. So Fg could act that way, where Fn would act this way. Now, we're going to get into a little talk here in a little bit about equilibrium and looking at how these forces balance. But in a flat surface situation, like I just drew, the Fg acting down, the Fn acting up are almost equal and opposite each other, which means that my block doesn't go this direction. It doesn't have that ability. It's just sitting there. It's at rest, okay? If I look at the situation on the incline, this weight is not on the same coordinate system as my normal, and then this blue arrow, which we haven't talked about yet. So sometimes what we like to do is we like to take these forces that are in various angles and make them all even on a set coordinate system. So typically what we like to do is we like to look at this in terms of components. Okay? So I might draw a component vector that would look like this, in which, in fact, here, let's see if I can change colors. Sometimes this works well for me, sometimes this doesn't. Ooh. Another part of my favorite thing about Empire Strikes Back, tauntauns, very cool. All right, so we're going to switch to a red color here. This would represent a component force of the weight in the, say, y direction, and this would represent a component force of the weight in the x direction. And again, it's based on these angles. So in other words, if I look at this incline has an angle right here, and generally we're given the angle of what our incline is. And that angle refers right back to this angle right here. There's some geometry that plays along with this that says that if I have this line and they're parallel and they're cut by bisectors or something along that line, I can look at it in terms of triangles. I get similar triangles essentially. So in other words, this angle right here is equivalent to this angle right here, and there's my right angle, and there's my right angle, and so I end up getting that these triangles are equal. And again, chances are you don't want the geometry proof of that, but it is that this angle here comes to this one here. In fact, that'd be kind of an interesting one, is to sit down and do that and actually show that they are truly the same. And again, I'm not going to take my time here, but I have done it in the past. All right, so again, when we look at normal forces, the normal force is the one that is perpendicular to the surface. In this particular case, my normal force matches a component of my weight. It doesn't actually act or the same as my weight. So you got to kind of be careful when you're looking at these to make sure that you're looking at your normal force compared to the weight component of that normal force. Normal force is something that has a tendency to always equal out whatever it needs to be. So in other words, the normal force changes as that angle changes of my incline. So it can get bigger or smaller depending upon whether my angle is increasing or decreasing. And then there's limits to that. And so the normal force is going to be the greatest when all of the weight is in balance with it, where in the other situation, as the angle increases, my normal force shrinks. Okay? And that should kind of make sense because my angle changes, which means that the side or my component force changes on that. So again, normal force is not a definite arrow all the time. It's a variable arrow depending upon how much weight is on a certain angle. Okay. The next force here is a friction force, and you got a chance to see a little bit about friction force when we were using the PhET simulator the other day. And that friction force is, again, one of these forces that kind of grows and shrinks with how much force we apply. If you've noticed so far in all my free body diagrams, this is the only force that's kind of acting in that direction. But if you just went back to the last picture, you know that there's a component that acts this way and then a component that acts this way. So we actually have part of my weight that is counteracting my friction. Notice the arrows are going opposite each other. Friction force actually can be calculated. It's based upon the two types of surfaces that are in contact with each other. We're going to do mu for your shoe, so that'll be one of those activities where we'll get a chance to look at various surfaces in contact and calculate a coefficient of friction. That's, again, my big word there is coefficient of friction. You may have to pause so that you can take time to write that down. But my friction force is equal to a coefficient of friction times a force normal. So in other words, there's a link now between my normal force and my friction force. But it changes as the surfaces change. Okay, so that's the key thing. The friction force can also change then as my normal force changes. So again, if I'm changing my normal force, I change how much friction I have. And when we start to look at this, we can look at will the block slide or will the block not slide, depending upon how much friction can be there and how much force parallel down the incline there is. So we start talking about this as being my force perpendicular and this being my force parallel, okay? And I didn't use those words in the last slide. Maybe I'll back up here just to kind of make sure that that's understood. But on my last slide, when I said that this was the weight force in the y direction, I will probably refer to this as the force perpendicular. It's perpendicular to the surface. And this one will be my force parallel because it's parallel to the surface. So I like to talk about them in terms of force perpendicular versus parallel. All right. So my friction force is, again, one of those things that we start to look at. And we're going to examine situations to see if things are in equilibrium or if they're not in equilibrium. All right, I think what I'm going to do is I'm going to kind of pause there. And then my next slides in the next video are going to talk about that big concept of equilibrium. But I really want to break this down to look at those forces and where those forces are kind of being in terms of my free body diagram. So tonight, know those types of forces. You may want to go back and review those, do some of the reading, and then we'll look tomorrow night at how those forces play in equilibrium versus non-equilibrium situations. And lab collection tomorrow, if you want to, you can preview. There's a video on the in-class part that tells about how we're going to use this program Data Studio and motion sensors in collecting some accelerations. So why don't you go ahead and maybe take a few minutes to just briefly watch that. We'll be able to watch it again in class tomorrow. But enjoy your evening, and remember, happy physics.